It's a pleasure to have virtually with us Steffi Baum from University of Manitoba. It's often fun preparing introductions because you learn lots of interesting things about people. Steffi's had a remarkably diverse career and was very well known for all her work on the connections between quasars and radio galaxies and clusters and the intracluster medium and radio halos, and also for her work on Hubble Space Telescope. She got her PhD in 1987 from the University of Maryland, and after a postdoc in the Netherlands at Twingelo, became, I think, maybe one of the inaugural class of Hubble Fellows in 1990 at Johns Hopkins. Then spent 11 years at the Space Telescope Science Institute in many different roles, including as the scientist for the Space Telescope Imaging Spectrograph, and she's still involved with James Webb and NIRCam. She spent 2 years as a senior science diplomacy fellow for the Department of State, and then 10 years as the head of the Carlson Center for Imaging Science at Rochester Institute of Technology. And since 2014, she's been the Dean of the Faculty of Science at the University of Manitoba, where she is now. She's won lots of awards, ranging from the Annie-Jump Cannon Award of the American Astronomical Society in 1993 to becoming one of the inaugural class of AAS Legacy Fellows in 2020. I would say, the award I found most interesting was the 1999 Rolex Achievement Award given annually to one female and one male college lacrosse player for career achievements supporting society. And she was indeed the captain of the Harvard lacrosse team and soccer team in 1980. And so, maybe all of that will come into play, but at least she's going to tell us the latest on activity in galaxies. So, and we will have our follow-up conversation tomorrow at 2:30 on the same link. So go ahead.
Okay, thank you very much for that introduction. I'm going to talk today. I've chosen to give you a talk which is sort of an overview of a field that is having a renaissance, looking at what may be the radio galaxies, powerful galaxies in their young phases as they're being born. So I'll give a broad overview to set the scene. This is a paper, so I have to get rid of you guys, sorry, so I can see my notes. Okay, this is just a figure from 2002, sort of explaining the overarching paradigm of active galactic nuclei. In the middle of a galaxy of some sort, you have purportedly a supermassive black hole. And here you can see the size scale in parsecs from 10 to the -5th, the size scale of the event horizon of a 10 to the 8th solar mass black hole. Around that is some kind of accretion disk, which is might be thin in some sources, might be fat in others, depending upon the magnitude of the activity. Beyond that, you have some kind of obscuring disk around the parsec scale. Along perhaps the rotation, the spin axis of the black hole is sometimes emitted a jet, which can move all the way up to near the speed of light. And on larger scales around that are emission line regions of various sorts, scattering regions, broad line regions, which are observed in various parts of the spectrum, the optical, the infrared, the X-ray, gamma ray. So that just gives you, of course, in the traditional paradigm, depending upon whether you're looking down the pipe at a super active source, you might be seeing a quasar. You might look along the side and see a type 2 quasar. And if it's a lower power source, then it won't be a quasar, but it'll be a powerful galaxy. Oops, now what happened? Okay, now I can't turn pages. Okay, so now the part I'm going to focus on is the powerful radio galaxies. And of course, as I noted, I'm going to be talking about the young radio galaxies that might not have reached their full size yet. But to understand them, we first have to get situated with regard to large scale radio galaxies, which are the more prevalent kind of radio galaxy that people have studied. So here's a radio optical image from HST and the Very Large Array. Here in the middle is the elliptical galaxy seen in optical light, made up of stars. And then coming out somewhere from in the middle of that are these long jets of synchrotron radiation, cosmic rays, spinning in magnetic fields, providing the emission, and moving rapidly out well beyond, you can see the host galaxy into the intergalactic and intercluster medium, where depending upon the power of the source, they either end in a hotspot, as you'll see in the next image, or they kind of fizzle themselves out and then inflate large lobes or create various shocks in the medium that you can see there. So the black holes in the centers of these galaxies are around somewhere between 10 to the 7, some n times 10 to the 9 solar masses. As I said, you get these jets feeding these very large scale lobes, reaching up to megaparsecs into the medium, and that's dominated by synchrotron radiation. So just to give you some understanding of the sort of logistics that are going on, the Eddington luminosity is the luminosity at which radiation pressure prevents further infall, and the bolometric luminosity, that is the radiative luminosity of these sources, can reach from 10 to the -4 to 1 times Eddington, sometimes super Eddington, but generally in that range. The radioluminosity, that is, that you see in these cosmic rays spinning in magnetic fields, are around 10 to the -3 to 1/10 of the total kinetic energy coming out of these sources. And the kinetic energy coming out of these sources, as computed based on the work that's going on in the environment from them, is comparable to the Eddington luminosity. And at any one time, when you look at galaxies, the luminosity function of radio galaxies shows that depending upon the luminosity, you have somewhere between 1 in 100, 1 in 1,000, 1 in 10,000, with the more luminous ones being rarer, of galaxies that are radio loud at any one time. And long ago, before we came to think that all elliptical galaxies have black holes in them, we didn't know whether that meant that there were nuclear black holes in only that fraction of galaxies, or now we believe that we have black holes in the center of all galaxies, but they're only active for a fraction of their lifetime. And the lifetimes of these powerful large-scale radio galaxies are somewhere between 10 to the 6th and 10 to the 9th years, depending, of course, on the circumstances and whether they're high or low power. Nothing do we know for sure. These are all the estimates we get from observations. And the mass accretion rates to power these sources can actually be very, very small, as low as 0.001, 0.01 solar masses per year, up into, for the very powerful quasars, up to 10 solar masses per year. So just setting the scene a little more about radio galaxies, I say they're not just butterfly collecting, just to remind myself that astrophysics and science in general tends to be faddish. When in the dark ages, when I was getting my PhD, which was some years after the VLA had come into commission, and when the VLA came into, Very Large Array came into commission, then there was a huge industry of imaging these powerful radio galaxies because they were very bright in the sky, and they made beautiful images, and we were learning all sorts of new things. Then at some point, all the reviewers got tired of all these proposals, and if you put in a proposal to image a radio galaxy, you got back a comment that it's enough butterfly collecting. But after a while, it's become realized again that the radio galaxies are not just interesting rare objects, but they're actually very important parts of the evolution of all galaxies. So they're back in vogue. So anyway, why is that true? It's true because we now understand that radio galaxies are constraining the total energy of the central engine, that is the kinetic plus radiative, which are comparable to one another. If we can understand the lifetime and stability of radio galaxies, we are learning interesting physics about the ejection axis, the accretion disk, the black hole physics. They're actually a very important source of magnetic fields and cosmic rays in the intergalactic and intercluster medium. And the interaction of the jets with that medium probes the medium and allows us to discern interesting physical quantities about it. There is a problem, which I'll talk about later, where our standard models of galaxy evolution predict many more massive galaxies than we see. And also there was a long conundrum where we didn't understand why all the hot gas and clusters didn't just collapse into the center. And powerful radio galaxies and AGN solve both those problems. And of course, because you can see them at high Z, they have long been obscuration independent signposts to the formation of massive bulges and black holes at high Zs. But we still have very little understanding actually of how they evolved during their lifetimes. So I just want to point out here in this image of Cygnus A taken with the VLA, it's a slightly different looking source than the one that I showed you earlier. In Hercules A, here's the nucleus, a one-sided jet. And then at the end of the source on both sides, you see hotspots, which is where the jet is banging into the unperturbed medium and accelerating particles in the hotspots itself. And then from those hotspots, there's a backflow into the intercluster or intergalactic medium. So it's a slightly different physics scenario in the high power and the low power sources. So like the black holes that launch these powerful sources, their host galaxies and their gaseous environments, they must be born, they must evolve, and they must die. So that's something that we have to understand. So now on to the compact small radio sources, which are the type of sources that I'm going to focus on for the rest of this source. So back in 1980, where there was a discovery of a new class of radio source that had this same structure I showed you in Cygnus, that which is on the hundreds of kiloparsecs level, but in these compact doubles, the structure is on tens to hundreds of parsecs level. And these are called compact symmetric objects, and they often have, as you'll see, convex radio spectra for understandable reasons. So it turns out that these small radio sources can be found by their spectral shapes, and a whole group of them were found in the main observing space of radio astronomy, about 1 gigahertz to 10 gigahertz. And these were dubbed the gigahertz peak spectrum, or GPS sources. And this is just a montage of some of this is frequency versus flux. And you can see them peaking, turning over around 1 to 10 Janskis. Gigahertz. If you look at their actual luminosity across the whole spectrum, they their peak luminosity, this is a nu F nu, is actually in the infrared. So like many large-scale radio galaxies, a lot of their radiative luminosity is in the infrared. Okay, so because us humans like to name things, and there grew up a zoo of names, a lot of historical baggage for these different sources as they were discovered in different ways. Sometimes there's a class of them called MPS, or megahertz peak spectrum sources, gigahertz peak spectrum sources, high frequency peak spectrum sources, and peak spectrum sources. I'm going to try and refer to these as peakers, but as I show from different publications, you'll see them called all sorts of things. The compact symmetric objects are less than 1 kiloparsec inside, and then there's a class of slightly larger objects called the compact steep spectrum objects, which are 1 to 20 kiloparsecs in size, still all well within the host galaxy.
And Steffi,
Yes.
peak in F nu, because in the
in,
previous plot.
No, peak in flux in Jansky's.
Okay.
And the peak in F nu is in the infrared. Nu F nu is in the infrared.
Nu F nu is in the infrared.
Right. That's not where most of their power is coming out, but that's where their radio spectrum is peaked.
Okay.
Sorry, I can't see if anyone has a question, so you'll have to cough loudly or something. Thanks. Okay, so here's a plot of, so it was understood pretty early on that there's some continuity in size and property. So here's the projected linear size in kiloparsecs. So these are 10 kiloparsec, these are 100 parsecs, 10 parsecs, and depending upon how big they are, you can see that there's a correlation between their intrinsic turnover frequency in Jansky's versus their size. So the smaller they are, the higher their turnover frequency. And this is roughly approximated by turnover frequency as L to the minus 0.65. And the mechanism for turnover we'll discuss next. So in most sources, the turnover mechanism is believed to be synchrotron self-absorption. Basically, these are very small sources, and so they're compact and they're dense. And as you go to longer wavelengths, you get the synchrotron radiation, the electrons, particles that are emitting the synchrotron radiation are absorbing the emission before it can get out, and that is what's causing the turnover. And you can, this is the kind of formal equation for the theory that predicts what the correlation then of some of these parameters should be. You can either just choose a standard B field and see what the correlation looks like. That's done here. Or you can use the equipartition field, which assumes equal energy in magnetic fields and particles. And that very nicely predicts these frequency correlations. So by and large, it's believed that the turnover is caused largely by self-absorption. But free absorption, thermal absorption also probably plays a part, at least in some sources. And there's a set of sources called the extremely inverted spectrum extragalactic radio sources, which is a class of the peakers identified by Gopal Krishna, in which the turnover in the spectrum is steeper than allowed by pure synchrotron self-absorption. And this is just a plot from their paper showing various models. The thermal material can either be mixed in or it can be in the screen just outside of the component. And that those fits here do slightly better. And so there probably are sources where the free absorption is also occurring. Now, what might we learn by studying these peakers? What are some of the interesting questions? Well, obviously, we want to know how, when, and where radio galaxies are born and what their early years look like. We would like to understand how long they live in their active phase and how much they flicker on and off. We can, because they're very small, they're interacting with a quite intense circumnuclear galactic environment, and that allows us to study those interactions up close and personal. Obviously, they have jets in general, and we can study the early evolution of those jets. We can try and understand whether high power and lower power sources have the same birth and evolutionary pathways. We think they probably don't, but we can study that at a young age. And as we said, we can consider how nuclear activity, kinetic outflow impact galaxy evolution, particularly in the inner parts of these galaxies. And obviously, it would be interesting as samples grow to observe how these things change with redshift. Okay, so what might these sources be? So there's a number of models, and there's probably some of these things going on in all cases, and we'll explore this further through the data. So obviously, some could be, and some probably must be, young versions of the large radio sources that will eventually propagate out to these large scales over their active lifetimes and become the typical large-scale radio source. But they can also be intermittent. That is, some could have very short lives. They could start and then sputter out and never make it to large sizes. They could be frustrated. That is, they may get stuck on small scales when they interact with their dense clouds in their circumnuclear environment. And there might also be some of them that are so-called frustrated imposters, where as they're trying to get out, their radio emission will be enhanced because they're being compressed. They're not expanding like a normal radio source, and therefore they may be boosted in power, radio power, and so we may be confusing them for a large-scale radio source, and they may never become those. So we'll explore some of these things next. So just to give you some more looks at them, there are many images of these sources that are out there. They come in really interesting and diverse types of morphologies, just as the large-scale radio sources do. So here's a source with a twin jet going in two directions. Here's a source where there's a nice jet early on, but it seems to kind of spiral out of control and dissolve. Here's a typical double lobe source with a hot spot on each end. And here's a source in which the outer emission is fading and there's just a little nucleus next that might be a dying source. So it's just to give you examples that they come in all sorts of nice forms. Okay, so how do we know that some of them are young? Well, this is easy and nice. Well, not easy, but observations with VLBI over a long period of time allows observers to track the actual motion of the hotspots, and therefore infer both the velocity and an age. So again, this is just one particular source, an example, VLBI images. So they're not easy to get, but they've been built up over a long period of time for good number of sources, tens of sources now. This particular source is roughly 100 parsecs, has the hotspots are moving apart at roughly 0.4 C, and the inferred age is 1,000 years. Okay, and this is from An and Bond 2012, and just shows a count of 20 some odd of these compact objects that have been observed in this way, and their ages determined, and you can see they range from very, very young up to a couple thousand years in age. And again, this is just, An and Bon also did some modeling, analytic modeling of how a radio source might expand, high power and low power sources, and compared that and put the known sources on those tracks. And the idea being, well, would it be consistent with a source grow? What would the power change in those sources be as they grew over time from parsec scale all the way up to the large scale sources? And you can see there's rough consistency there. And similarly, they looked at how the sources might evolve in the linear space regime over time. This is their velocity versus their linear size, to see if models could give some support to the idea that these are growing and evolving sources. Okay, so we think that some of them are young and that they're evolving, but in fact, we also know that perhaps that they're sources, large-scale sources that have new activity going on in their center, and I will show you some examples of that now. So, yeah.
Can I ask with these 1,000-year lifetimes? I mean, are the total numbers reasonable? I mean, that we should then have 1,000 times as many million-year-old sources, and
yeah. So what happens?
Are they really that rare? Are
what
they rare enough for that to be okay?
Yeah, I'll come to that later. What turns out is there's a flattening, that it works pretty well, but there's a flattening of small sources. You get too many of the smallest sources. And so you have to evoke some of these other possibilities, not that they're not young, but that they're not all the sources you're categorizing in this way are actually going to grow into big sources. So yeah, we'll come to that. Okay, so this is, again, just a particular source that, to give an example of this is a large scale radio source. You can see the outer part, and these are the so-called double sources, where you see an outer part that's fading in brightness, but within the nucleus, when you do high scale observations, VLBI observations of the nucleus, you see that there's a little source, a double, which if it wasn't embedded in a large scale radio source, you would probably characterize as one of these peaker sources. And there are others of these going back in time that have been observed. This is OQ208. Which is a source here that has a kinematic age of about 255 years. When you observe it at lower resolution, and you start to pick up old steep spectrum component here, which is probably a relic of previous activity. These images are just of this little part here to show you what kind of detail you can get from the new part of the radio source, and the different components are moving at slightly different velocities as they move out in these complex sources. And this is just another example. This is 0258 plus 35, again, a kind of dying outer large scale radio source, but embedded right in the middle of it is a compact steep spectrum source, one of those little active sources that's approaching tens of kiloparsecs in the inner part of the dying galaxy, the dying radio galaxies. So we know some of them, we know there's intermittency. We don't know the statistics of that yet. So we also have stated that they're interacting with their environments, and we have lots of both statistical and detailed studies showing that. So in these compact steep spectrum objects, the peakers, there is a higher asymmetry between the brightness of the two lobes than you find in the large scale sources. So this is the flux ratio between the two lobes from various studies. Here are the so-called large scale radio sources, which tend to have be similar in luminosity between the two lobes. Even if the jets are dissimilar, the lobes will be similar, and the jets are dissimilar frequently due to relativistic beaming. But you can see in the smaller sources here, 10 kiloparsecs, 1 kiloparsecs and smaller, you get appreciably bigger asymmetry ratios. You can also study the polarization properties of some of these individual sources in detail. The polarizations tend to be, fractional polarizations tend to be low, but they're still studyable, and they show signs of strong Faraday rotation measures at different points in different sources, which can be studied in detail. In this particular source, I'm not going to go through all this in detail, but there's a sharp curve. Here's the nucleus up here. There's a sharp curve and bend in the jet right around here, and there's a strong rotation measure in the gas, which is well modeled by mixing at a sharp bend. Okay, there's also an alignment effect in the compact steep spectrum sources that have been well studied. These are the sources on the 10 kiloparsec scale, roughly. And all of these sources show emission line gas, which is strongly aligned with the radio source itself. And that alignment is stronger than is seen, say, in the low Z large scale radio sources. So in most cases, the emission line gas lies interior to the radio hotspots. And as I'll show in a minute, the gas is shock ionized in this. So this is a particular image of 3C303.1. Here's the continuum with the lines embedded in it. Here's the lines only in O3. And here's the continuum only showing an elliptical galaxy, and the radio source you can see here superimposed is right along this axis. And that's a common kind of configuration we see. So just a little model of what's happening here. These are, again, analytic models from just describing what people believe is happening. There's a jet that's going out. It has around it a turbulent cocoon, which is creating a contact discontinuity with the outside ambient medium, which is shocking the medium and causing the emission lines. And this is just a slightly more complex model that has the jet with a dentist drill and bow shocking clouds as it goes through the medium. And these are additional models of what you might expect in X-rays as a jet evolves. And these are early in the life, 100 kiloyears or so in the life. And you see that the prediction is that the X-ray, there will be X-ray emission, shocked gas, which will evolve along the same axis as the radio source. And this is exactly what you see when you look at some of these sources. Again, most of these sources, this is 3C305, another CSS source. And the radio is shown here in these, in the green. The nucleus is here. There are jets that go in two directions. And then the source is disrupted at these two ends. And then you get these big, long, low surface brightness plumes in the radio, and the red is here. Let's see, which one is that? This one, the red here is the X-rays. And here in the bottom, you see the green, I believe, is the X-rays as a contour, yes. And the red is the O3. So you can see that you get this confluence of shocked 10 to the 4 degree gas, as well as the hotter X-ray emitting gas all along the radio axis.
Steffi, can I interrupt you for just a minute?
Yes.
We had a question from Sukanya.
Oh, yeah, sure.
Steffi, I think I missed, what is the typical redshift of these sources?
Oh, well, they're found at all redshifts, but the well-studied ones are, you know, maybe around 0.03, 0.06.
Okay, great. Thanks.
Okay, so this is just another example. This is 303.1. And again, in contours is the radio, and then in the red and the color is the X-ray, but this particular source also has a spectroscopy, which shows that this is in fact shocked gas that you're looking at in the X-rays, and you know, not synchrotron or something else. Okay, so these sources also have been observed to demonstrate jet-induced star formation. This is a composite of HST-UV images. And overlaid, so the optical, this is optical images with UV in the color. The contours are optical. And then over here, the contours, I'm so sorry, maybe a little hard for you to see, but the contours are radio. And then they're overlaid with the UV, which is the star formation. And you can see clearly the alignment of the UV, the star forming stars are aligned along the radio axis where the interaction is occurring. You can also get IFU, so spectroscopy of all the pixels in the emission line regions to figure out what is the motion of this gas. This is a particular observation of 3C303.1, this time looking at the O3 kinematics. Here again is the radio source and the gas aligned in that direction. And what you see is there's broad lines and there's narrow lines component of the O3, and both are exhibiting outflow, red, blue, in these sources. So these are, you see that there's shocked outflowing gas. Okay, so if you want to think that these peakers or some fraction of them may actually become these large scale radio sources, then there's some properties which you would hope would be continuous because they don't change on the time scale of the evolution of the radio source. So that's an important thing to look at. So here I'm looking at some of these properties. This first one is the size, the projected linear size of the source. Versus, let's see, now what are we looking at? Versus their luminosities, their rest frame mid-infrared luminosities of these sources. And okay, these sources down here, these pluses are low luminosity, they're not as powerful as the other radio galaxies on here, and they're put in for comparison purposes. Up here in the stars are the QSOs. These are only peakers on this. Oh no, I'm sorry. These are peakers and large scale sources, with the stars being quasars and the triangles being narrow line sources. And here they are out to 1,000 kiloparsecs, and then the smaller ones here. And what you can see is that they're roughly along the same lines. So if you're a narrow line radio galaxy, whether you're small or big, you have roughly the same, there's continuity in the power, your total luminosity, your radiative luminosity, and same for the quasars. So there's consistency. There's also well-known correlations of radioluminosity or power with X-ray luminosity or power, so we can look at where the peakers fall compared to the large-scale radio sources here. Here, FR1 is a large-scale radio source, FR2 is a large-scale radio source of higher power, so here are the FR1s, here are the FR2s, and then we can put on the same plot the powerful peakers and the less powerful peakers, and we see that they follow similar relations in this plane. Okay, another thing to look at regarding the central engines is this the same one I just showed? Yeah, this is just another way of looking at that same plot. This is the X-ray luminosity versus the radioluminosity shown in a slightly different way. And you can see that there's a slightly different correlation for low power sources and high power sources, but the size, they're independent of the size on those correlations. So that's—
I have one more question from Roman.
Yeah.
Steffi, I have a question. Is X-ray luminosity for these sources measured over the same scale as the radioluminosity? That is, it's just coming from these lobes?
Yes.
So it's not the whole galaxy, it's just the lobes themselves?
No, it's the total radioluminosity, so it includes the central engine. Yeah.
Okay, thanks.
Okay, another thing that doesn't have much time to evolve, if these are young sources becoming big sources, is the black hole mass. So one would like to see whether the inferred black hole masses and Eddington ratios are roughly similar for the peakers and the large scale quasars and radio galaxies. And again, here you have the size of the object versus the inferred black hole mass, right? These are all measured from, inferred from lines, not direct measurements, obviously. And similarly here, the ratio of bolometric to Eddington luminosity. And again, all you're looking at here is that there's continuity of property of the different kinds of sources, not dependent on size. Okay, so here now we're looking at the host galaxies, because again, we don't think that the host galaxies are evolving very much on these time scales. And this is a standard way of looking at the properties of the host galaxy ellipticals, which is looking at the power law of the brightness distribution R/1/n versus the effective radius in infrared data. These is NICMOS J and K data. And these are just the standard lines that divide between normal and bright galaxies. These galaxies up here are the so-called brightest cluster galaxies, the biggest galaxies, the big fluffy guys who live in the middle of clusters of galaxies predominantly. And that here you see in triangles are the hosts of FR2 galaxies. That's a large scale radio source. The CSS sources are sprinkled in here, and the GPS sources are sprinkled in here. And so basically what this is showing is that we have not yet found many peakers corresponding to the big cluster BCGs, though that's not too surprising because those are rare. But we do see that their properties of most of them overlap very nicely with that of the other sources, FR2s, compact deep spectrum sources, FR1s. These are mostly the FR1s. So what is different about them? They're not all the same, but there are some things that may be different in the in the peaker sources. Many of them have substantial star formation rates ranging from tens to hundreds of solar masses per year. It's not clear yet whether they have significantly more star formation than larger sources, but there have been studies that suggest that's true. And this is just a histogram of the number of the star formation rate for peakers inferred from the either far infrared luminosity. Some cases there's more than one estimate combined. And you can see that there's kind of almost a bimodal distribution. These are just for the peakers. Now, we do know that these compact sources have a higher rate of star formation for a given molecular mass than a normal star-forming galaxy. So this is a plot of the mass of molecular gas versus the star formation rate. And this line would indicate that the gas would be depleted and turned into stars on a 10 to the 9th year time scale. And you can see, therefore, that these compact sources typically are burning stars at creating stars, burning molecular gas into stars at a considerably higher rate. Now, another thing that's different in these sources appears to be the amount of atomic hydrogen, at least the detection rate of that atomic hydrogen and the optical depth of it. The H1 detection rate of compact sources is about twice that of the extended sources. Of course, it's a little easier to detect absorption against a bright nuclear source. So some of these things need further confirmation. There are also compact sources, as I noted, with large amounts of molecular gas. There are also ones without so much molecular gas. Once again, you see kind of a bimodal distribution. In this case, you're looking at the molecular gas content of these peakers. Again, there's a suggestion that they may have more than large scale sources, but that's not statistically confirmed yet.
So your molecular gas inferences are coming from emission, but your atomic gas ones are coming from absorption?
Well, there's both in molecular gas. Yeah, they're detected in emission and absorption. Yeah. And yeah, so again, there are various ways to infer this, right? You can directly observe molecular gas like CO, right? You can infer it from a dust observation and also from X-ray estimates. Okay, so a little bit about feedback and why it's interesting. Feedback is a huge topic, and I'm not going to attempt to go into it in gory detail. at all, but just to show why it's become a very important topic, and then to show you the kind of detailed studies that you can do in these peaker sources. And I'll give you one example of that. So the fundamental problem that was realized is that galaxy modelers were predicting many more of these big massive galaxies than were actually being observed. And these are plots of galaxy luminosity functions from Croton to 2006. And the prediction from the models is this kind of whatever dashed line here. The data is, as you can see the data, these are at two different wavelengths, I believe, yeah, K band and J band. And what you can see is without any kind of energy injection to prevent the creation of these very large massive galaxies, you overpredict the number of massive galaxies by a large margin, whereas models that inject energy inflow from the AGN AGN heating to prevent the collapse can do a better job. So the mass of this, as people all know by now, this is the plot of the mass of the central supermassive black hole to the mass of the galaxy bulge, which is studied in a whole host of ways now. This is from
Marilyn has a meeting from 12 to 1 and then 1 to 2. So she said maybe you won't eat together for 1.
Someone, should I be quiet? Hello?
Go ahead.
Okay, sorry. So this is the basic correlation that was understood, that all bulges have some kind of black hole in them, and in fact that black hole mass is correlated with the mass of that bulge, and how to have such a fine-tuned system over so many orders of magnitude requires some kind of feedback loop, was realized early on, and the AGN is one potential source for that, and that's another motivation for that. The other area, which maybe it's on the next one, no, the other area that, as I mentioned before, is in clusters of galaxies. There was the conundrum of why doesn't all the hot gas fall in onto the central galaxy? And it's become understood that in large margin, that's because of the kinetic outflow from these active galaxies in the center, preventing that inflow. Okay, so let's look at some of the signs that there are these shock ionizations, these shocks going on in the centers of these galaxies impacting their evolution. So these are just plots of radio source size versus diagnostics of shocks in the emission line gas. Now, largely emission line gas in AGN is photoionized by the nucleus and its bright accretion disk. And so you can see in the large scale sources out here, the diagnostics and out here suggests that is what's happening. Those are photoionized. But when you look at the smallest sources, you can see the diagnostics indicate a significant impact from shocks. This is the source I'm going to go into a little more detail on to show you what kind of studies can go on. This is 4C1250. An old favorite of mine from my thesis. It's a peaker, this is just the optical spectrum. It's a narrow line radio galaxy that has high excitation emission lines. In this source, you've detected a mass flow, which is largely in molecular glass, which has been heated up to 400 K. You can estimate the kinetic energy of that outflow, and it suggests that about 3% of the jet power from the central source is going into accelerating that molecular gas. So this is just showing you in the dust SED of this source. Here's the radio, and then you have this big peak in the infrared that you model as this hot gas. So here's some detailed observations. Here is, here's the nucleus in this source. This is the radio. You can see this S-shaped source here, and here it is at much higher resolution. You can see the very narrow jet flowing into this hotspot here. And the gas is detected here and here in this source. What you're looking at here is the H1 components. Okay, so the H1 components, as we saw, are spatially separated, and they're also separated in velocity. This blob here is near systemic, whereas this blob is moving quite rapidly, blue shifted at the end of the southern lobe.
And is this H1 in emission or absorption?
This is H1 in absorption.
Okay.
You can't, yeah, there's not enough signal to get it in emission, right? Yeah. So here it is. This is the outflow part, and here's the systemic part. So the blue shifted H1 is going up to 1,000 kilometers per second. Okay, so there's also CO observations of this source, and there's CO emission as well as a CO absorption, and there's a systemic component as the same as the H1, and then this is the outflow component in the CO, again, superimposed on the H1. So there's an atomic and a molecular outflow. And that outflow is also seen in emission line gas. This is the O3 profile, and you can see the O3, the broad component, these are just the fits to it, showing that there's a similarly outflowing component in O3. So there's a lot of, through hard work, you can get these very beautiful detailed observations. And then you can also look somewhat at the statistics of the outflow in these peaker sources. So in roughly 22% of sources that have O3 detected in the Sloan spectra, you find that they actually show these blue wings in these peaker sources. And roughly the same percentage also compact sources with H1 absorption also show a blue wing with outflow velocities above 100 kilometers per second. And the blue wings in H1 absorption, as shown here, tend to occur above a certain radio power. So this is a plot of the velocity of the component, H1 absorption components, and you can see, and this is systemic, and you can see at low powers, relatively low powers, you're not seeing these large outflow components, but at the higher radio powers, you start to see this increase in velocities. Okay, so let's talk a little bit about what these are again. And if they are young, what do they grow up to be? And so as I've tried to describe, the radio morphology and luminosity of these peaker sources are similar to those of the large scale sources. They live in the same host galaxies as the large scale radio galaxies. They have AGN bolometric luminosities similar to the large scale radio galaxies, similar far IR properties, and similar X-ray radio correlations. For various reasons that I don't have time to go into, confinement by the ICM seems like an unlikely scenario, because when you try and model these things, you don't find a sufficient confinement to prevent them from escaping. And as we noted, we believe that they must be young, at least some number of them, because we can measure their ages based on their outflow velocities. So we can ask whether there's a modeling which suggests that, again, these are analytic models looking at where things fall on the radio power versus projected source size. This is a bit of a complicated diagram, but what is these are tracks of evolutionary tracks under certain assumptions. And the idea is just to show that from these small scale to these large scale sources, depending upon these are the high power versions, that they are likely, they could well evolve into the high power or Van and Raleigh class 2 large scale radio galaxies. Similarly, the lower radio power ones would evolve into the plane where the FR1s or the lower power large scale radio sources lie. So this was the question that was asked before. There, you can look at these questions of, the numbers and, are there too many, too few, based on their ages, et cetera, to evolve into these sources. And this was done way back when we first started looking at these. And what you find is, in fact, that the prediction would be that they would follow this kind of a path, but you get, this is the old plot, there's better data, but it shows the same thing. You get a surfeit of these sources, a flattening at small size. And so you need something else to also be going on. And the modeling suggests that could either be these intermittent sources or sources that turn off and turn on too rapidly to evolve into large scale sources, or a subpopulation that's completely disrupted on small scales. Oh, so sorry, this is the same thing again somehow. So where am I going? Oh, I went the wrong direction, sorry. Okay, so there people have tried to model some of the physics involved in some of these things in terms of the stability of an accretion disk when it's accreting, and that this was done largely to try and explain X-ray AGN that don't have optical emission line nebula. And so their argument is that the central engine has turned off on a time scale which allows the emission lines to fade away, which is a 10 to the 5th kind of time scale. And so the argument for those sources is maybe there's some kind of intermittency that turns off the central engine, and it might be due to some instability in the accretion disk. And basically, if you want to build a larger scale radio source, if the outburst lasts 10 to the 3 years or less, it's very hard to then allow that source to expand beyond its host galaxy. So that might be an explanation for why some of these fade away. Okay, so just to summarize the interesting and overlapping possibilities for what these sources are and the pros and cons, I'll finish up with that. So one model, as we said, is they're young and growing radio galaxies, radio sources, and I certainly believe some of them must be. They have similar host galaxies. They have continuity of properties. The proper motion timescales show that they are young, of whatever else they are, and they're plausible evolutionary scenarios. And somewhere out there have to be the progenitors of the large sources. But as I said, there are too many small sources, so not all of them can become large sources. So some of them may be transient or short-lived sources, and that would provide a solution to the numbers problem. There's, as I suggested, some other evidence for short time scale behavior in AGN. And we have examples, which I showed you, of sources which were large scale sources, which turned off and now have a second epoch of activity starting in their nuclei. But we don't really understand the physical basis for the lifetimes, what turns them on and off, and in what circumstances that would happen. Another scenario is that they're frustrated, that they can't make it out of their host galaxies. They get disrupted on the way out. And as we know, there is evidence for some massive cold ISM in some sources, but not in all sources. So it could only explain some of the objects if we see evidence that they're being disrupted. And then there's the class of imposters, which probably also exist, where due to confinement, the total radio luminosity is enhanced. And so we bundle them into to think they will evolve into these powerful large scale radio sources, but their central engines are probably intrinsically weaker. And their radio luminosity is being enhanced. And we know, for example, that happens for large scale radio sources in the centers of clusters, that their radio luminosity can be enhanced from confinement. So to summarize, what have we learned? Compact radio sources or peakers interact strongly with their ICM and their host galaxies. Some of them are likely to be the progenitors of the large radio galaxies and quasars. Others could be short-lived and possibly repetitive. Their interaction with the environment may boost the radio power and star formation in some of them, creating a group of imposters. And the key to understanding these objects is the systematic sample studies and detail for large samples to get the statistics, as well as detailed multi-wavelength studies of individual objects coupled with modeling. And through this, we are learning a lot about radio source as well as galaxy evolution. So if you're interested in these things, the 6th workshop on compact deep spectrum and gigahertz peak spectrum radio sources is going on in Torun, Poland, well, online actually, next week. And I invite you to check out all the activity and new results coming there. Thank you. Okay, oh, there you are. I'm done.
Thanks very much. That was a wonderful review and lots of exciting new results. So we have time for a few questions. So Kanya, do you want to start?
Thanks, Steffi. So if you were to compare it to the distribution of quasars, which peaks around redshift 2, do these peak at lower redshifts then, or?
So again, I would say that there's not enough data on them, right? Because the samples, but what I didn't get to talk about very much is the samples are really increasing, right? And that's why you develop these different classes of them. When low frequencies of radio arrays came online, you started seeing the ones that peaked at lower frequencies, right? And in the millimeter now, you can observe them and see them at higher frequencies. And of course, there's a redshift, the peak will move with redshift, right? So to get good statistical samples, I think is that we don't have them yet to answer those really interesting questions that you're asking about, which are quite interesting. But they're found at all redshifts. It's not that we don't have them at all redshifts. It's just that, we don't know the number information well enough.
The redshift distribution yet.
Yeah.
Thank you.
Can I ask a question, Steffi?
Sure, Jim.
Early in your talk, you alluded to jets coming out of the black hole. Now, do these jets, and the black hole is spinning, presumably, are these jets perpendicular to the equators of the holes, or don't you know?
Well, I think we don't really know, right? They're models of what's going on, but we don't have sources where we know the jet axis and we've measured the spin axis, right? And so we can say, yes, that's what's happening. So it depends if you're asking from a theoretical perspective or an observational perspective.
You can either.
Well, I mean, theoretically, people would say that's probably what you would expect, but observationally, we don't know, I would say.
Okay.
I wanted to ask about the relation between the intermittent and frustrated. In that, so in the frustrated case, why isn't the frustrated just a way of making the lifetime short? Or is the idea in the frustrated case that the things appear to be young, but they're not because the proper motion isn't actually giving you the correct age?
Yeah. The idea in the frustrated case is that they'll never make it out, right?
Right.
Because before they can make it out, they'll be trapped, right? So you're saying, so yes, so then as well, I don't think that would affect your estimate of the age of those, but the question of whether they will evolve to be the large scale ones, you would say they might not make it, right? They might get disrupted before they can get out.
Okay, so they would still be short-lived things,
yeah,
but short-lived things that aren't going to become they aren't progenitors of big things.
Right. So so that would change the balance of small to large things, basically, right?
Good. Rachel?
Thanks, Steffi. Great talk.
Where are you?
So
There you are.
as you as you mentioned, the energies are more than sufficient to quench cooling and make quenched galaxies, etc. But there's a bit of a fine-tuning problem when one tries to simulate in detail how the jet actually interacts with the cooling medium, as you know very well. And it seems that one needs the jet to have very specific properties, in particular, sort of the lightness or heaviness, so the ratio of the mass loading to the energy loading. And another very interesting possibility, I think, that's been proposed recently is if the jets have significant cosmic ray content, that could help solve this fine-tuning problem. So are there prospects for constraining those jet properties observationally?
Well, that's a good question. Let me think about that. Yeah, so these questions of what is the main energy transfer mechanism, if you can say it that way, right, have actually been around for a long time, right?
Yes.
And so I'm trying to think back to how those things. I don't know. I mean, so it's a good question. I think the constraints are coming from, as you said, the problem, and this is the same thing with the cooling flow problem long ago, right? I mean, even if the jets are coming out like this, right, on a narrow, but you have to inflate the entire, otherwise it'll just pour in along the other axis, right?
Exactly.
So one of the mechanisms for that, of course, is the diffusion of cosmic rays and the magnetic fields. And I think some of the interesting things that there was early on a lot of work done, but not so much recently, has to do, is studying the Faraday depolarization, looking at when you look at lower frequencies in these sources, you tend to find a much bigger envelope, right, of radio emission than the narrow envelope. Mm-hmm. And tracing the nature of those larger scale, the older cosmic rays, if you will, and studying them is probably a good place to look. And there's a lot more of that's been starting to happen with Westerbork and GMRT and things like that. So that's probably a good place to look.
Great, thank you very much.
Okay, I think we will stop there for today. And anyone who would like to dive in further, please join us tomorrow at 2:30 on the same link. And we can ask more questions. And thank you, Steffi, again for a fabulous talk.
Okay, maybe I'll see you in person one day.
Yes.
Take care.